Hi class, we're going to walk through these calculation examples dealing with light energy. We should be able to do these types of problems and solve for either energy, wavelength, frequency, or number of photons. So in this particular example, we're talking about a laser emitting green light. So what is given here is the wavelength of 523 nanometers, and we know that most of the time we're going to need to be dealing with this in meters. So there are 10 to the 9th nanometers in 1 meter. So this would be written as 523 times 10 to the negative 9th meters. We are asked to find energy, and from our data sheet we have this equation for energy. E of a photon is equal to h nu. And we also have this expression for c, speed of light, is equal to lambda nu. So what we know is that there is a relationship between energy and wavelength. If we simply rearrange this c equals lambda nu equation, we can solve for nu, then plug in up there to get E is equal to hc over lambda. And this is the energy of a single photon. And I also want to point out that the energy of n photons is equal to n times hc over lambda. And so we should be able to use this form of the equation for all of the questions in this video. So we just need to plug in to find the energy of one photon. So the energy of a single photon is equal to h 6.626 times 10 to the negative 34th joule seconds. Units are super important. It will often help you determine the unit of your final answer, and sometimes can help you solve the problem if you're unsure about how to solve. Looking at the units can give you a clue. The speed of light is in meters per second, and then the wavelength 523 times 10 to the minus 9th meters. So we'll cancel out the meters, the seconds, and we'll be left with joules, a unit of energy. Plugging this in gives us 3.80 times 10 to the negative 19th joules. And we know this is joules per a single photon. So this per photon is not necessarily required notation, but it is not incorrect, and it can help you remember that moving forward, because the next question is, what's the calculation for energy of 1 mole of these particular photons? So one way of solving this would be just to do a unit conversion using our mole conversion. Joules per 1 photon, and we know that there are 6.022 times 10 to the 23rd photons per mole, and that would give me 228,882 joules per mole. And because that's such a large number, often these are reported in kilojoules. So to take 228,000 to kilojoules, we're going to divide by 1,000 joules, and we will get, after rounding for significant figures, 229 kilojoules per mole. And so that is the answer we're looking for. We could also say the energy of n photons is equal to n times hc over lambda. And n here would be 1 mole of photons. 6.02 times 10 to the 23rd photons times Planck's constant, 6.626, times 10 to the negative 34th joules seconds times the speed of light, meters per second, all over the wavelength, 523 times 10 to the minus 9th meters. Cancel our units. We are left with joules the same number as above, and we can say this is per mole because this is photons per mole here, and rounding 229 kilojoules per mole after the unit conversion. So either way you want to do it would work out fine, and I just wanted to show you both to give you an idea of how that looks. And the final question here, if the laser emits a certain energy, how many photons are emitted? Well, here we're going to be solving for n, so we can rearrange the energy of the photons multiplied by the wavelength divided by hc. So you should be able to do the algebra to rearrange that equation, and then we'll plug in here the energy 1.30 times 10 to the negative third joules times the wavelength 523 times 10 to the negative ninth meters divided by Planck's constant 6.626 times 10 to the negative 34th joule seconds times the speed of light 3.0 times 10 to the 8th meters per second. So we'll cancel out my units that I can. Everything cancels out, so we're left with n, which is just a number of photons, and this calculates to 3.42 times 10 to the 16th photons. Now, with all of these, you should be checking your answer, just kind of logically thinking about it. Number one, you cannot have less than one photon, so it is not possible to have a number that is times 10 to the negative number. We'll call it negative y. You cannot have a negative number. Can't be less than one photon. Okay? The other thing you need to think about is, well, what was the energy of a single photon? It was on the order of 10 to the minus 19th joules. And so we would need a significantly higher number of photons to generate this much energy, which is 10 to the 17th times larger than the energy of a single photon. And so the number of photons that we should get would be on the order of 10 to the 17th. It's 10 to the 16th. We also have to account for that number out in front, that 3.42. So that's where the difference is accounted for.